So someone asked me when is the exam. I think if you go at the bottom of the schedule, no? So if you look, I think in coordinates, yes, there is a PSU final exam, and this is a winter 2017, and this is a day classes meeting before 4, and first class meeting is a Monday at here between no, is Monday 11:30, is this one, right? So check it there, don't trust what I say. All right, everyone agrees? All right. So, we use graph for a large variety of problems. And for example, they are very useful for games and puzzles. And games and puzzles say, well, who cares about them? But actually, very often model complicated situation, and from that, learning to use that on something simple is the first step on using on something more complicated. Do people know the missionary and cannibals puzzle? Goes also from other names. If you go on Wikipedia, it's telling you the story. You go back 1,000 years or more. And the thing goes this way. You have a river, you have a boat, and here 3 missionaries and 3 cannibals arrive there. And then there are 3 cannibals. I distinguish them by making the head square, so you know. And so they have to cross the river, and the boat holds only 2. So 2 people go there on the other river, and then someone has to bring the boat back, and bring there another one, back, and another one. And if at any point on one side, on one bank or the other bank of the river, there are more cannibals than the missionaries, the cannibals eat the missionaries. So you cannot have that. Alright? So now, if I tell you, solve this one, how do you go about it? So, an easy way is to build a graph that represents the situation. Right? So what is a good representation? We think about the initial bank of the river, and we represent how many missionaries, how many cannibals, and whether or not there is the boat. Alright? So initially, what do we have? 3 missionaries, 3 cannibals, and the boat. Right? So now, what are the possible things that we do? We send on the other side 1 missionary. Right? So, what remains on this side of the river? 2 missionaries, 3 cannibals, and no boat. Right? This is very bad. Right? And so, we could send there what? 1 missionary and 1 cannibal? And what do we have on this side of the boat? 2, and no boat. We could also send there 2 cannibals, right? And then what do we have on this side? 3 missionary, 1 cannibal, and no boat. Alright? And there are others that I didn't write there. And then from this one, I will have a bunch of possibilities, yeah? And it's possible that here I get to the same again. This is why it's a graph, right? And so if you build this one here, even on a piece of paper by yourself, in 5 minutes you solve it. It's not that complicated. And of course you can write a program that constructs this graph, and the program is going to solve it. Yeah? And so if you know what is a graph, if you know how to represent it, you can write a program that solves this one. The problem is relatively simple. And there are many others. Do people know the game of tic-tac-toe? Tic-tac-toe, you play on a board like this one, and a place put a note or a cross, and the goal is to put 3 in a row. This is not a very smart game. Only small children enjoy it, because then you know exactly what's happening. And so you start with an empty one, and here you build a graph in the same way. Here, if cross is the first, you can put a cross here, or a cross here, and every other one you get it by rotation or symmetry, so there are not many more. And from this one you put the other move, the circle, and again you remove all the symmetries and the rotations. You build the entire tree. It doesn't take very long, and you convince yourself that the first player, if it is smart, is never going to lose. And if the second player is smart, is never going to lose. Of course, if you make a bad move, yes, of course you are going to lose. And so these are possible uses of a graph. There is another one interesting, and is to make mazes. You see, this is a maze. Can you see it, or is out of the page? And so there are algorithms that do this on the fly. This creates the maze. And so this one uses a graph and a concept that I'm going to explain in a few minutes. So this is just to tell you that there are many interesting uses of graphs. All right, so let's go on. A graph and a binary relation are the same thing. Two different ways of seeing. So let's recall what is a binary relation. Who can tell me what is a binary relation? We gave a very precise, very terse definition. When
you cross one set on itself.
So a binary relation on a set A is the subset of the Cartesian product A cross A. So it's a bunch of pairs of elements of A. Yeah? Some people completely forgot this. Alright, and the final is comprehensive. Also because a graph and a binary relation are the same thing, and so we have to remember what a binary relation is. And so if we have a set A that contains the element small a, small b, small c, and small d, a binary relation is a subset of A cross A. For example, you can have AA, AB, BC, and CD. All right? So this is a subset of the Cartesian product. It's a bunch of pairs. Now, how can I represent them? I could say, look, I have A, B, C, and D. And which pairs I have? AA, which is this one, AB, which is this one, BC, which is this one, and CD, which is this one. You see now that you have a graph? Do you remember when we made binary relations that we were concerned whether they were reflexive or symmetric or transitive? So if you represent it as a graph, it's very easy to see, for example, whether it is reflexive. What do you expect to make it to see it reflexive? A has a loop on A, B has it on B, C has it on C, and D has it on D. Everyone has a cycle to its side. This is a reflexive. What about symmetric? If you have an arrow or an edge A to B, you need one B to A. Right? And what the transit? If you go from A to B and B to C, you need an arrow A to C, straight. And so by looking at this one, we can tell immediately that this is not reflexive and not symmetric, not transitive. And if I ask you, change it as little as you can to make it reflexive or symmetric or transitive, from the graph it is relatively easy to do. And so two sides of the same coin. Sometimes we prefer to look at it in one way, sometimes we prefer to look at it in the other way. All right, the final thing that I want to do today is to talk about the spanning trees. What is the spanning tree of a graph? Sorry, you don't see anything. What is the spanning tree of a graph? Is a tree that has the same nodes as the graph, and it's connected. So you can go from every node to every other node. So one way to make it in your head is to get rid of the cycle. Right? So how do you get rid of the cycles in this case? You said that disconnect A to? Yes, F from E, but you can also disconnect A from E, right? Or disconnect A from B. All right? Now we'll give a criterion, but basically you can do it arbitrarily. Spanning tree is important when you have, say, an electrical grid. You need a wire. If this is a bunch of houses in a region, you need a wire from each house to any other house to make sure the electric power reaches everyone. Maybe the same with the water supply. All right. So we compute a minimal spanning tree when we have a graph which is undirected and weighted. And so we wanted the tree where the cost of all the arcs together is the smallest. So there are two algorithms, and I have an animation. So should we look at the animation? I'm sorry? Undirected, yes. I don't hear anything. Say it again.
Spanning tree of this graph.
All right, thank you.
This algorithm works on a weighted graph, and we know it's a weighted graph because there are numbers associated with each one of these edges. These numbers might reflect perhaps a cost to go from vertex D to vertex E, or perhaps it could be the distance or some other kind of numeric value. The minimal spanning tree is a set of edges. All these edges need to touch all the vertices of the graph, such that the total length of all those edges are as small as possible, so they are minimal. That's what makes this a minimal spanning tree. Not all the edges may be used in the minimal spanning tree, and in fact, there might be more than one minimal spanning tree for a given graph. So here's how it works. Since it's going to touch all the vertices, you need to start with one of them. So it doesn't matter which one you start with. I'm going to pick H to start with right here. And the next step is to find all of the edges coming out of that vertex that go to vertices I haven't been to yet. So in this case, it's going to be this edge 3 that goes to I, 4 that goes to F, and 4 that goes to E. Find the one that's the lowest and highlight it. So that's the one with 3. And I'm also going to highlight the vertex that it goes to. That's vertex I. So now we repeat, but this time we're going to use the set of all the vertices that I've now visited. So that's H and I. Find all of the edges coming out of those that go to vertices that I haven't been to yet. So that's the 2 here going to G, the 4 going to F, and the 4 going to E. Find the lowest one. That's the 2 going to G, highlight it, and we're also going to highlight the G to indicate that we have now visited that one. Repeat. So we've got the 4 going to A, 6 going to B, 5 going to F, the 4 going to F from H, and the 4 going to E from H as well. Now since there's a tie, we've got the 4 here going to A, the 4 going to F, and the 4 going to E. It doesn't matter which one we pick one at random, so I'm going to pick the one going to F. I'm going to highlight that one. This is what we have. Do this again. 4 going to A, 6 going to B, 5 going to F from G. I'm sorry, we don't do that one because we've already been to F, so don't consider that one. How about the 3 going to D, the 3 going to E, and the 4 going to E from H? Looks like we've got 2 to pick from, both these 3 here. So I'll pick the D, that one. And highlight D. So we'll repeat again. Looks like it's going to be the 2 going to B from D. Like that one. And then we'll look again to see the edges coming out of these nodes. It looks like it's going to be the 2 going to A, the lowest one. Now look again. We've got a 3 coming out of D going to C, and we have a 3 coming out of F going to E. All the other ones coming out of all my red nodes here are higher. So let's pick C. One coming out of D going to C. And the last one to pick is going to be this one going to E from F. So at this point, all of the nodes have been visited, so that means we now have a minimal spanning tree. So I should be able to hide the original graph, and you can see that that this middle span tree doesn't use all of the edges. Nevertheless, it does visit all of the vertices. And let's go and let's just add up how much all of these pan out to be. So we've got the edge CD with a weight of 3. We've got BD with a weight of 2. We have AB with a weight of 2. Looks like EF, 3, FE with a weight of 3 as well. GI, 2, IH, 3, and FH, 4. If we add all these up, we've got 5, 6, 7, 10, 13, 14, 15, 18, 22 as the weight of our minimal spanning tree. So as I said, the output of the algorithm is set edges with feet. So here is the set of the edges C, D, E, D, A, B, E, F, F, E, G, I, H, and F, H. That is a minimal spanning tree. And you can probably see that there were some places where we could have come up with a different minimal spanning tree. Like, remember, it was a third step or so where we had a choice between this edge with 4, this with 4, and this with 4. I hadn't picked the one going from FH, but I could have just as well picked the one going from HE or from GA. And that would have resulted in a slightly different minimal spanning tree, but would have ended up with the same minimal weight of 22. So you can see that there were probably other places where I could have made a choice, but we would have ended up with this same number. So there you go. That's how to do Prim's algorithm to calculate a minimal spanning tree on a weighted graph.
All right. So here there is another example where you can test your knowledge. So let me say in simple words, maybe I'll talk a little bit with my hand, but it should be helpful. How this works. You separate the nodes in the one that are in the tree and the one that are not yet in the tree. At the beginning, no one is in the tree. At the end, all of them are in the tree. And every time you add one. How do you add one? This is the key of the algorithm. Right. Initially, you put one there at random. You pick whichever you want. So if we want to do this one, I pick D. So now that's the graph. Now D is in my tree, and everything else is out. Now I pick one node in my tree, one node out, such that the connection is the shortest. So after I pick D, what can I pick? One is to be in my tree and one out, and the connection is the shortest.
A, E, or D all have equal weight.
This is the only one. This is the only one that allows you to connect from the one you have to the one you have not yet. So I will pick this one. Now I have these two in my tree and everything else is out. Now I want to connect one in my tree with one out, and I pick the shortest edge. Which one do I pick? B. Fantastic. So now I have D, E, B in my tree and everything else out. I want to pick one from my tree and one out and connect them, and I pick the shortest edge. Which one is the shortest? A, 1. And I keep doing this one until I have all the nodes in my tree. Yes?
The top one is your graph, correct?
Yes.
D is connected to A, B, and E, right?
Oh, yes, sorry, I didn't see. You are right.
Okay.
All
so
right.
you could have
Yes.
just as efficiently gone D to A, D to B.
Right. I could have picked any one of those.
Okay.
Yes. Sorry. Yes, I didn't understand what you were saying. Yes, that is the graph. Fantastic. This is free. It's considered a greedy algorithm because it doesn't look very much. Just pick the shortest to add one more. And you say, well, now you add this one because it's very short. But if you had a longer one, maybe at the end you will get a better deal. And it doesn't happen. Alright? So this is free. Now we look at another way to do the same job. Kruskal. Alright, this is short to start. I don't know why.
Hello everyone. Today we'll find minimum spanning tree with classical algorithm. Classical algorithm is implemented with disjointed sets. So my previous video on disjointed sets is a prerequisite for this video. In previous video we have talked about disjointed set and how it operates. But we haven't talked about how disjointed sets can be useful. Today we'll use disjointed set to find the minimum spanning tree of the graph. What is minimum spanning tree? So this is the graph that we have. It has a bunch of vertices and a bunch of edges. Each edge has a weight. The minimum spanning tree is a subset of edges that connects all the vertices in the graph, and it has minimum total weight. So in this case, the minimum spanning tree is CF, AF, and AB, because they connect all the vertices in the graph, and they have the minimum total weight. So the problem we want to solve is, given a graph with weighted edges, find its minimum spanning tree. Today we'll use classical algorithm to find the minimum spanning tree. And classical algorithm utilizes disjointed sets. Recall that disjointed sets has two operations, find and union. Find will take an item and then return the disjointed set that item belongs to. And union will merge the two disjointed sets of these two items into one disjointed set. So now let's talk about the classical algorithm. We define A. A is used to store all the edges of the minimum spanning tree. So initially A is empty and eventually will return A. Then for each vertex of the graph, make a disjointed set with that vertex. So each vertex will be used to create a single vertex disjointed set. And then sort all the edges by weight increasingly. So the edge with smallest weight will be in the front, and the edge with biggest weight will be in the end. And then for each edge that connects V1 and V2, the smallest edge will be taken first. If the disjointed set of V1 is not the same as the disjointed set of V2, then we push that edge into A. And then merge the disjointed sets of V1 and V2 into one disjointed set. Now let's use this example of graph to walk through the algorithm. First, we take the edge with smallest weight, which is CF. And since C and F do not belong to the same disjointed set, so we go ahead and merge them and push the edge into A. And the next one is AF, which has a weight of 2. And again, A and F do not belong to the same disjointed set, so merge them and push them into A. Next is DE. DE do not belong to the same disjointed set, merge and push to A. Next one is CD. Note that C and A belong to the same disjoint set, and DE belong to the same disjoint set. So C and D do not belong to the same set. So again, merge them and push to A. Next one is FE. Now A, F, C, D, E all belong to the same set. So FE belong to the same set. So we should not push this edge into A. Next one is AB. And AB do not belong to the same set. So merge and push. Now we have a spanning tree that connects all the vertices, and we believe this spanning tree has the minimum total weight. Now let's look at our code. Our graph is a
All right, we don't look at the code, of course. Instead, we try to do it on this example to reinforce the concept. So if I talk with my hand again, how can I explain this algorithm? Imagine that every node is an island. And I want to bridge all these islands together. So what do? I find that the shortest bridge that connects the two islands which are not connected already. So now this is a bigger island because you don't have to swim to go from one to the other. You can go over the bridge. And so you start to make islands which are a little bit bigger, and every time you connect the two islands which are not connected. And which bridge you use? The bridge with the shortest cost. How is different from the one before? The one before, you grow an island and everyone else is outside. Here you can grow an island here and an island here, and then you bridge them. You see the difference? And they work. Was there a question? All right, so let's try to do this one. At the beginning, I have A, B, C, D, E, F. These are 6 islands completely apart. Right? Now I look at all the bridges, and I want to connect the 2 islands which are not connected yet with the shortest bridge. So then the bridge there is 1, 2, 3, 4, 4, 4, 4, 5, and 7. So the first one that I bridge are what? AB. And so now I have a bigger island here and 4 separated islands. Right? So now I look at the next shortest bridge. What is it? B is 2, BE, yes. And I bridge this one. So now I have a bigger island, which is this one, and 3 separated islands, right? And you keep doing this one until you have your so what is the mathematical notion of these islands partially connected? Maybe you remember equivalence classes? A lot of stuff in this course, right? Well, we have the notion of equivalence classes. Each island, as these things grow, is an equivalence class of nodes. And if we want to bridge 2 different equivalence classes, once we bridge it, we put everything in the same equivalence class. So we start with a partition of this one, which is the finest, and we end up with a partition which is the coarsest. And we talk about a fine and coarse partition. Now, it's not that you have to have those notions to understand the algorithm. But of course, that is a very nice and a very expressive terminology for this. All right? So let's see what we covered today. What are the key points of this lecture? No one wants to tell me? So we saw some algorithms, right? What are these algorithms? Dijkstra, Prim, and Kruskal, right? Dijkstra computes what?
Shortest path.
Oh, yes. All the shortest paths from one node to every other node in a graph. All of them. Right? Prim and Kruskal computed the same thing. Compute a minimum spanning tree. Alright? What else did we look at? Path and cycles. Yes? And in particular what? Euler and Hamilton. Alright? So these are the key things we discussed today. Now you say, why do I need those things? So, let me tell you a bit about myself. Some 30 years ago, I was a student at the University of Maryland, and I was working for the Postal Service, USPS. That was before the internet. They were making a lot of money. A lot of mail was going through. Now everything is electronic, the checks, everything, letters, communication. And so they had these envelopes, third class mail. This is what you call it junk mail, which is advertisement. And this the address is typeset because it's printed. And then there is a lot of stuff on the envelope. Reply today, you want $1 million, trip to Hawaii, and all that. And they had a machine that was able to read this one, but because there is so much junk, the machine was spending a lot of time reading all this junk before finding the address. And so they said, if we could tell where is the address without reading, because reading was expensive, without reading, we would make a lot of money. And so the idea is that if you have an envelope, how do you spot the address on the envelope? Without reading. So I did this experiment. I got a letter, with the computer, I got an envelope. I changed every letter in a black box. Then I went around the department to professors, students, staff, and say, where is the address? They couldn't read any. 100% that they found where is the address because you see it on the end. And so, how do you write a program that without a reading knows where is the address? So this is a typical envelope. You have some stuff here, and this is the address, and you know it. Then you have some stuff here where is the stamp, because in the stamp there are letters. Here there is the sender. And then here, big, there are all this junk everywhere. You want $1 million, reply today, and blah, blah, blah. And so the problem is, how can you draw a line around all this and say, this is what you have to read to find the address, and forget everything else? And so, this was a variation of Kruskal. With the variation of Kruskal, with 100% accuracy, I mean, the machine didn't make a mistake, not one. He never found an envelope that the machine would get it wrong. Would do that. And so this was a variation of Kruskal. And of course, I'm not going into details because it's too complicated. But of course, if you don't even know what is a minimum spanning tree, and if you don't know the Kruskal algorithm, you can't do something like that. So this is a motivation to study this stuff. Say that again? No, not on pixel. I would have a box around a character.
Oh, the box.
Right. so each character was a node of the graph. I would compute the complete graph, all the distances, and then I would start to build the minimum spanning tree. And when you build it, you have these bridges from one another. And all the bridges here, all the cost here is small. This is really is a few pixels, right? And then you have a big jump from here to here. This is 100 pixels. And this is a 50 pixels. And this is 200 pixels. And so you look at the distribution, you find a million that are a few pixels apart. And then you find 3 or 4 which are 50 or 100. It's very easy to find at that point. And so and now you have the 4 blocks, so not only I was able to look at the average, but I knew exactly where the sample was. So the machine could look at the stack and see whether the sample was right. Or having the sample and all the jump. Say it again? Yes? Yes?
We do that with data file. From where we do that with data file from where we can also
Can you do this with
data files
data files?
where we make it with a certain format and then when you scan for information instead of the person editing.
I don't know. Well, all right. So they can talk if you want to leave. I think the lecture is over. Yes.
Prime and crucible.
Yes.
So first graph that you had was this,
Yes.
and then when I did the crucible algorithm, I chose 1 and then
Yes.
2 and then 4 and then 5,
Yes.
become all the way to 16.
Yes.
And for print, when I chose B,
Yeah.
I will get number 1 first instead of 4 and 2 because it's the shortest.
When you do prim,
Yes,
you start from A.
B.
You start from B. Yes.
Because 1, 4, 2,
Yes.
I get 1, and then from A, I get 3 and 4, so I choose 3.
So this is a prim.
Yes.
So with prim you have to connect. Thank you. With prim you have to connect the one that you have with the smallest edge. So here, if you have A and B, what is the smallest from A and B that gives you something outside? These two, not these three.
Okay, I see.
Yes. Yes, bye.